Hi, my name is Rami Khalil. I'm the co-founder at Liquidity Network. And today's presentation will be about a variant of our NOCUST protocol that uses zero-knowledge proofs to prove consistency of what's happening. So first, a brief intro to off-blockchain transactions. So could you please raise your hand if you're not familiar with any second-layer solutions such as payment channels or Plasma or NOCUST? No hands raised, so everyone is familiar.
Can you repeat the question?
If you're not familiar with second-layer solutions, could you raise your hand?
If you are familiar.
If you are not. Again, no hands raised. Okay, so I'll still go through a brief intro. So if you're doing transactions on the blockchain, you essentially throw your transaction into the mempool and then hope at some point that it gets included in one of the blocks, and then you get some kind of confirmation on its inclusion in the blockchain. So one downside of this is that you have very high latency on the guarantee of finality of or the guarantee of inclusion of your transaction. Essentially, you can throw in a transaction with a very low transaction fee and then wait forever and never get it included. In off-blockchain protocols, you do all your communication directly with a known peer. So in payment channels, you know who the counterparty is in the payment channel that you're using. In a commit chain-based protocol like Plasma or NOCUST, you know who the operator is that you're communicating with. So essentially, you can have low latency on some sort of guarantee that this transaction is going to eventually be included in one of your blocks. At, of course, the cost of delayed finality of this transaction, because eventually this operator needs to submit a transaction into the blockchain, and this transaction needs to be included and needs to include your transaction. But it's all a matter of responsiveness, at least from my perspective, because you want high responsiveness in whatever applications, whatever wallets, or whatever user experiences that you're trying to achieve. So a rough taxonomy of these solutions would be commit chains and channels. Commit chains would be something UTXO-based like Plasma, where you have accounts and you have spent coins, and you basically have a small Bitcoin-style ledger. An account-based ledger would be NOCUST, and we're basically here. We're going to talk about why applying zero-knowledge proofs to one of these protocols may actually improve its security or give you better guarantees. And this is a very rough taxonomy. Don't take it too much to heart. I know there are some things missing here, but I just want to give you an outline of where we are. So what is the rough life cycle of a commit chain? This generally applies to something that is Plasma-based or NOCUST-based. Essentially, you have the central operator, and this operator gathers a few of your transactions and commits a single block to the chain that enforces all of your transactions. Of course, the less data this block includes, the more cost-effective things are and the lower value payments that you can make. Without zero-knowledge proofs, without any guarantees by some verifier algorithm, you sort of see protocols include this challenge and response phase, where the block is proposed and essentially no challenges against it sort of just implies that it's correct, that everyone knows what the data behind it is, and no one really disagrees with what's inside it. In terms of NOCUST, we have periodic commitments, and there is a timeout period where anyone may efficiently dispute any data inside the commitment sent. And first, I'll just go through a brief introduction to vanilla NOCUST, no zero knowledge, prehistoric times, nothing special going on. At the very core is just a data structure that allows us to then build some reasoning around accounting. What is balance? What does someone own? What do they exclusively own? And around that, we can build a challenge response game to ensure honesty of the operator under any circumstances. And then, given all these factors combined, we then have a secure protocol for actually making off-chain payments at, well, zero gas cost such that the operator only submits a constant size checkpoint that aggregates everything, and if there is anything wrong, a user always has the power to retain custody of their accounts and ensure that their balances are consistent and everything. So breaking this up into smaller pieces, we basically first create this part where we just give meaning to the data. We give data representations. We define what balances are like, what transfers are like, what users are actually like. In this model, balances are actually intervals exclusively allotted in a tree. Transfers are simply a set of transfers that are then committed to with a Merkle set. And users are their respective Ethereum addresses. Then we define what consistency means. What are the goals of this protocol? So I won't actually like throw a giant Merkle interval tree at you in a slide. I just want you to think on a high level that we have a set of goals that we want to achieve, and then all these data structures and all these ways to achieve them basically come later. But we have to be solid on exactly what are the security goals that we want to reach, such that when we actually do reach them or we don't reach them, we know how we're reasoning. So in terms of consistency, for payments, this is really straightforward. You have correct accounting. Whatever I am debited with, I am actually debited with. Whatever I have received in some way or the other, I actually get credited with. So my balance increases and decreases, logically. Valid authorizations, nothing happens to my account in terms of debits without my authorization. So I have my own custody, basically, self-custody. In NOCUST, this is a bit more intricate, because self-custody also requires that the owner of the account knows the state of the account in the commitment after every commitment. So there is a periodic check that the client comes and does and receives only the leaf that is relevant to them in this Merkle interval tree. And then we want to actually enforce all these nice consistency rules that make us have custody of our own accounts and for things to make sense. In vanilla NOCUST, we do this through two types of disputes and allowing users to solely rely on the parent chain, which is the blockchain in this model, for exits. So the first kind of dispute is an integrity dispute. So one thing that an operator might try to do is debit you for the transaction that you authorized, but never really credit the recipient. That has its own dispute mechanism. And the other one is an availability dispute, where that just makes sure that you know the data that you need to guarantee yourself custody of your funds, no matter what this operator does. Goes offline, gets hacked, explodes. And with the parent chain exits, you can always leave without anyone's permission, so you are the custodian of your funds. So these are the building blocks that we're going to play with and then add some zero knowledge to, so that we can maybe get rid of some of them in the enforcement or make things better. So the first challenge is to really look at this and then decide what is actually worth verifying zero knowledge and what would that even give us in terms of guarantees or in terms of reaching our security goals that we define. And we can really look in the middle and look at the consistency criteria. So we can, if we can ensure valid accounting, if we can ensure transfer delivery, and if we can ensure custody, then great. And when I say that, I mean if we can ensure it upon submission of the checkpoint. So what we would do is basically define some constraint system that would validate all these things given a zero knowledge argument. When the verifier is given a zero knowledge argument, that the operator can satisfy. So some questions we ask ourselves when we want to shift this protocol into something that actually utilizes zk-SNARKS or zero knowledge proofs in general. We still haven't decided if we're using SNARKS in this talk. Is what do we actually gain from the verification? So what do I want to verify? Do I want to verify correct delivery? Yes, that's something that would be nice, because then I can get rid of one of the enforcement mechanisms. I don't need to dispute transfer delivery anymore if I know that commitments just satisfy this constraint system. What are the drawbacks? So there can actually be drawbacks to using zero knowledge proofs, and the most straightforward one is that you have to generate the proofs. And if you're using a protocol like NOCUST, you actually have zero gas cost for your payments. So you can actually do not just microtransactions, you can go to nanotransactions and send less than what one gas is worth. So if you have to spend a lot of CPU time, or hopefully sometime soon GPU time, to compute these proofs, that might add to their costs, and then you have this lower bound on what is cost effective to transmit. And then also you have to orchestrate some trusted setup if you use certain SNARKs. Reiteration, so once we've introduced some of these nice constructs, what can we just get rid of? Remember back here we had a very nice core of an interval Merkle tree that actually lets us build all of these things. But that is also added complexity. It's not as straightforward as a simple Merkle sum tree or as a simple Merkle tree, right? So maybe we can get rid of some of these things, including enforcement. So this is what NOCUST could reduce to once you actually introduce some consistency guarantees. You don't have to deal with intervals in your Merkle trees or even sums in your Merkle trees anymore. You just have to deal with Merkle trees where the leaves only represent some account with some state, which is the balance. Your enforcement doesn't rely on a consistency dispute anymore. It just includes a ZK proof along with all of your commitment submissions. And then, the challenge response game reduces to only a game about data availability because you have consistency. Is everyone following? If there are any questions, please feel free to directly interrupt me or raise your hand if you're not too much of an interrupting person. So, right, this is just challenge number one. What is useful? Like, what do we want from this protocol? And what is useful to put in zero knowledge? Challenge number two, choosing an effective scheme. So there are a lot of things out there. And when you look at the blockchain as this really sensitive resource that you have to pay a lot to use, or that you don't want to exhaust, or that you want to increase the scalability of, you sort of come to the conclusion that as of right now, SNARKs are really the most cost-effective in terms of the verifier way to do things. So number one, at least these are the criteria in my opinion. You might have different opinions, and that's fine. That's just a matter of difference of design philosophy. So in terms of verification, it really all boils down to the gas cost. You can express this in multiple complicated terms, such that how long is the argument? Is it constant sized? Is it correlated with the size of the constraint system or the statement? But it really boils down to gas cost, in terms of Ethereum at least. And proof generation, how much does it cost to generate a proof? How flexible is my proof generation process? In the first slide, I mentioned responsiveness as being something that is important. And if you're at the engineering level, at the end user engineering level, you want to give that user signals that indicate that something is going on, something is being processed. And you want those signals to actually be meaningful. You don't want to give fake signals and then have your system crash and then none of those signals make any sense. So that actually matters how you're generating the proofs. Are you generating a really giant SNARK that will take you half an hour, or are you generating small pieces that you put together and then you can sort of affirm the last state that you've reached? Also in terms of cryptography, what are your setup assumptions? So this is not straightforward. So you could be able very easily to orchestrate a setup using an MPC like Zcash did, or you might not have those resources. So this is something you also put in mind. Are you willing to pay some of the other costs just to use something that doesn't require a trusted setup, or are you willing to do one? And also, once you do this one, are you worried about quantum security? Are you going to be working with a blockchain, or are you just going to send proofs to some counterparty? You take a lot of these factors into your design decision. And the primitives employed. Also, what are the assumptions behind the SNARK or the STARK that you're using? What do you trust, what you don't trust, what you think will be broken in a few weeks, days? So then we reach an intermediate state where we, at least for NOCUST, we say, okay, we're mainly concerned about blockchains. We want to keep the cost as low as possible. So it's mostly a matter of enabling even the smallest nanotransactions that your browser might want to pay to a website for a single visit. So we reach this, this new NOCUST with ZK-SNARKS for enforcement. which was previously just some ZK proof that we haven't decided yet. What is the third challenge? So efficient statements. So your consistency rules, you might take them and you might express them in some very straightforward language that then boils down to a constraint system such as R1CS. And some of the recent things or the really popularly used things that have come is that you're able to construct certain operations efficiently, such as hashing or signature schemes or encryption, by generating even an elliptic curve for the scalar field in your SNARK. When I say generating an elliptic curve for the scalar field, is anyone not familiar with the terms that I'm using? I guess I haven't attended the previous 2 talks, so I guess those must have been really good because you know roughly what I'm saying. So one nice example is actually generating this curve. This was first proposed by Ahmed Kozba from Berkeley. Zcash employed this as Jub. I understand also there's also now baby Jub for Ethereum's BN curve. And this allows us to do a nice commitment scheme, Peterson hashing, and also verify Edwards curve signatures. And then there's also MIMC, encryption and hashing, which given the right parameters gives some nice guarantees. So this is actually, this is a bigger challenge than one slide. This is really the difference between, am I going to respond to my user in an acceptable amount of time, or am I going to go generate a really long proof that will take forever? And how you approach this challenge really affects what the usability of your protocol and what the cost effectiveness of your protocol will end up looking like, or your implementation of your protocol, to be more precise. So let's say we apply some of the nice things that we have just seen in the previous slide, and we go with Peterson-Merkle trees, which is just Peterson hashing, and then you do it in a tree style. And you say that you're going to use EDDSA signatures and not ECDSA signatures, or not the native blockchain signatures. Maybe the native blockchain is EDDSA, but maybe it's a different curve. So you take into consideration that you're going to express your consistency concerns in the most efficient and cost-effective way possible. And by that I mean you reduce the number of constraints in your constraint system, or the number of gates. And then you have to operate in a flexible manner. So this is something that Coda uses a lot and was proposed by Ali Ben Sasson from Technion. And it's referred to as proof aggregation or cyclic recursive proof composition. And it really gives you in your design a lot, or in your implementation of the design, a lot of added benefits. Mainly, let's look at this first one, being incremental. So this is really more fault tolerant, because you might spend a lot of time generating a really large proof and then some server somewhere disappears, and then all of the generation that you've done is really lost. But if you have intermediate small steps that you're taking, you can sort of revert back to the last really small proof that you were concerned about. And a smaller memory footprint. So this machine that is going to crunch out your really strong SNARK doesn't have to include like 100 gigabytes of RAM just to give you what you need. You can do this on smaller machines.
The way you're doing the design work, are you actually developing your own zero-knowledge protocols, or are you just taking what's existing, knowing what the limitations are of each method, and then just using those as a sort of out-of-the-box to build a program, to build your system? Or are you taking both approaches?
I would say 90% taking what is pre-existing, 10% making what is pre-existing actually adequate for our needs. So we're not competing with Jens Groth, for example, in the next SNARK verification protocol. We're mainly concerned with the protocol design level, where you're actually making something that is employed and makes sense. And the way you design that also affects your security and a lot of other factors like usability and cost effectiveness. But Right, so if that was unclear, the main concern of this talk is taking what we established as already a secure protocol and saying how we can improve its guarantees, how we can support more things with it using pre-existing zero-knowledge proof work. Right, so from a design perspective, when you rely on recursively composable proofs, you can also increase your parallelism. You can do higher throughput and lower latency. Remember that small signal that I mentioned? You want to give to your user a small guarantee that says, I have received your transaction, or I have included your transaction in something. If that something is a really small million constraint proof that you can generate in a small amount of time, you can give back that signal, and then actually that signal means something. It means a small proof was generated and it can be aggregated upon further. You can achieve higher throughput because if you, sorry, go ahead.
I would like to wait for you to spit by. I'm not quite clear what it means to recursively compose.
So you can, if you specify a statement, for example, that you want to then translate into a constraint system, this statement can say that the following 10,000 transactions are valid, or it can say that the following 1,000 transaction is valid. If you don't intend on using recursively composed proofs, then you would say these 10,000 transfers are valid, and then you would simply send in the proof for that statement. If you intend to use, this is a practical example, if you intend to use something that can be recursively composed, you would then take the proof that one transaction is valid, the proof that another transaction is valid, and then combine those into a proof of knowledge of a proof of knowledge. And then you can do this in a sort of a hierarchical manner, and then you don't have a limit or a bound on the number of proofs that you want to verify. You simply keep going up one level for every set of transfers or set of transitions.
2 or whatever each level.
2 or 3, depending on what you do or what you see is efficient. All right, so we were parallelism and then we went to versatility. Also, this is the viewer bounds argument that I was saying. I don't have to know upfront exactly the bounds on how many transfers I'm going to verify or how many state transitions I'm going to verify. I can simply keep going along as long as I can, as long as I don't have to submit my checkpoint right now, or simply as long as I can do. And of course, this implies sort of lower costs. So if I were with a rigid system where I have to prove a few 100 million constraints, but I'm only interested in proving tens of transactions, then I have to pay the cost of generating this proof for this very large empty commitment or block. And maybe I don't know how many users I would have at first. Or maybe I don't want to predefine constants and then find myself really uncomfortable with them. Which these concerns really aren't done justice by just 2 words, but I'm trying to be as brief as I can. So it's not only about recursive of cycles of curves. You can also have a bound depth of recursion. So you might know that you're only going to go, if you think of the set of transitions that you're going to combine together as being combined in a tree-like manner, you might want to predetermine the depth of this tree. This is sort of like somewhere in between unbounded recursion, bounded recursion. It has its advantages when, for example, you don't have the nice cycles of elliptic curves that let you do unbounded composition. So then we go to a version of this old protocol that then uses this unbounded recursive structure to not have to predetermine beforehand what it's going to do. It can just flexibly accept as many users as it wants, as many transfers as it wants, and then only have to do processing that is as much as the workload. Proof generation that is as much as the workload. Then you run into a giant wall of compatibility. For example, Ethereum. Right now, the working version of NOCUST that is deployed is on Ethereum. So this would be our main concern. There are only precompiles for...
You mentioned about recursive debt.
Yep.
How much are you offering for recursive debt?
How much am I...
Keep you going? Is it infinite like quota, or do you have a limit for that?
No, so we're using the cycles of curves that let you do unbounded composition. I believe there is a protocol that is using the limited depth, but I don't recall it fully at the moment. Right, and then when you try to actually bring all this stuff to production, when you try to push out a nice set of code for people to use, you run into compatibility issues where the precompiles or the natively supported operations by the blockchain are not really there to let you do what you want. So in our case, for example, when we use unbounded recursive composition, we need to work with MNT elliptic curves. And Ethereum only supports BN elliptic curves, specifically the alt BN elliptic curve through precompiles. So it's still not the end of the world. One plausible solution is to just implement our own our own smart contracts and then do all of these elliptic curve operations. Another non-intuitive route is to actually verify one MNT proof inside a BN curve-based snark. And then there's also the native signature scheme, and this is more of a headache not just because of verification, but because then whatever application that you introduce then has to take care of creating signatures in a whole other scheme than what is provided by the infrastructure from the blockchain. So you just have more work to do. It's not really a protocol design, but it really slows you down in terms of what you can push out and how easily it can be done. Any questions so far? Excellent audience. Either you're very good or I am making a lot of mistakes and you're too shy to tell me. So other challenges that I have not given any talk about, I've not given any attention, is, for example, privacy mechanisms. So these open-ended zero-knowledge proofs that let you compose a statement, whatever statement you want to do, are very lucrative for creating privacy solutions. Because essentially you can only show, you have a public part, you know this, you have a public part in your zero-knowledge proof, so essentially you can only show commitments in that public part, and then you can sort of have your operator work with proofs and then be able to modify your account state with those proofs being their authorization to do so. So generating privacy mechanisms would be a very interesting design perspective to look from. Data availability guarantees. So in NOCUST, for example, there still is the data availability challenge, right? Because periodically you need to come in, you need to retrieve your account state, and then you need to go away until there's another commitment. This can be also alleviated by just posting the data on-chain, basically, or reduce like the minimal amount of data that you need to post on-chain so that you don't have to worry about data availability guarantees anymore. But then you also have gas costs. So it's a matter of which would you prefer, zero gas transactions or some transactions that have a fee associated with them, and what the user is really comfortable with, and of course, how these operators of these protocols actually end up looking like. For example, data availability might not be too much of an issue. You might find random operators that are crashing every day. Some operators might be, some operators might be known. So for example, an operator could be a famous tech company, and then you're fine knowing that this tech company isn't going to lose all of its data. Because really, if you think about it in the worst case, the worst thing that an operator can do right now is lose data to an account that it can never claim the funds of. Because if every commitment that the operator posts is consistent, then it can't just debit your account and take your funds. So there's no incentive for the operator to actually act against you. Censorship resistance. This is briefly touched upon in another protocol, also from Liquidity, called TEX. And zero-knowledge proofs there are used to sort of alleviate censorship, potential censorship, and also federation. By federation here, I'm sorry, I don't mean federation of the users. This is very clearly managed by the operator. I mean federation of who the operator is itself. At some point when you try to reason about the protocol, you see that the operator having actually an identity is no longer of any value, because alongside every commitment, some proof has to be submitted that this commitment actually makes sense. So if some random person comes in and submits a valid commitment, good for them, we just made one more block, it's fine. Unless we have worries about race conditions and unless we don't want to really reason about reaching consensus of on what the next state update should be. And on the implementation side, of course, faster provers. Right now, we're using CPUs pretty well. GPU implementations, things with some pre-computations for the scalar multiplications would be good. There's a lot of work that can be done here. Code Ahead has, I think it's still running, a challenge on building a fast prover. I believe the last thing they reached was something that is 3 times as fast as the libsnark, as the native implementation libsnark, and snark-friendly gadgets. So this is really a matter of what building blocks do you have before you have to start worrying about defining your own constraint systems just to do smaller operations, or what you would consider smaller building blocks, like verifying a signature or performing a hash operation. And formally verified tools. I have not personally seen this so far, but for example, libsnark, Zokrats, I just haven't seen like any formally verified tool that produces R1CS systems or does the computations required for the proofs or things like that. And of course, this gives you some peace of mind. One other thing that is kind of interesting is actually verifying that an R1CS constraint system actually models some problem. All right. That is my talk, and thank you for your time, and thanks to Consensus and the organizers for this great event. If anyone has any questions, I'm right here.
My question is probably going to be a bit redundant. It was a bit echoey when you were talking, so that's why. Can you explain a bit the operator's role again? And also, can you clarify in what's the role of the operator in context of the no-cost commit and whatever?
All right.
And then also, after that, if you can clarify what are some possible attack vectors when using this operator model? Thank you very much.
Sure. Okay, so the role of the operator is to basically make communication easier. So when you look from a communication perspective, a blockchain is a really distributed system, and you have to convince everyone inside on the total order of things. The operator here simply does this without being so much of a burden to do this. So the role of the operator is to only collect your operations and enact them in such a way that
it's more like a node then.
It's
more like a node rather than a miner.
Yes.
Okay.
So one term that is also used is relayer. In things like meta transactions, it's simply a central point or some simpler entity that you can communicate with, and it can reach a faster ordering on whatever it is you're trying to do, whether it's payments or smart contracts. The attack vectors. So without zero-knowledge proofs, so in the vanilla NOCUST version, attack vectors are basically denial of service and spamming the blockchain. There isn't much beyond that. Beyond that, everyone has pretty good guarantees on their account.
Can you somehow convince the operators to misbehave in any way, in some weird bribing or some weird, insert some perverse incentives in any way? Is that possible?
If you do, you will not. So we don't even trust the operator to behave honestly. If the operator behaves dishonestly, you always have a way of shutting down that operator, reverting the last checkpoint, and taking your last consistent state. It doesn't matter what the operator's incentives are.
Okay, cool. Thank you very much.
But with zero-knowledge proofs, of course, this scenario of the operator messing something up intentionally or unintentionally isn't really possible, because the checkpoint will just be rejected because there's no accompanying proof that it's fine.
What's the financial motivation for the operator to do his job and commit and send his proofs to the chain?
Fees, or you can also create a side protocol that gives it some similar mining reward. The incentive structure for the operator to do its job right here doesn't really affect the security of being able to commit a block.
What's your stack written in, and do you see it changing in the next 6 months or a year? Like which language, which frameworks? Does that, do you have multiple options, or?
So on the smart contract side, our stack is in Solidity. The only thing we have changed so far is just the version of the compiler and how compliant we are with the new additions. Will the smart contract level change within the next year or six months? I don't believe so. On the server side, we are mostly using Python. And will that change in 6 months or a year? Yes, definitely. We would like to shift away to something that is more efficient. On the client side, we are not going to change anything. Basically, we are working with a library that lets us release both Android and iOS versions for the mobile client. Yeah, there is the mobile app that you can download on the Play Store or the Apple Store. I should have put logos for that. But we don't see that changing either. But the component in this application that actually is related to the protocol that is mainly written in TypeScript, and that probably will not change either, because even right now, a lot of more support is coming out for performing elliptic curve operations in JavaScript, and that's just fine.
I think a lot of people here knows Plasma and other Plasma variants. Could you give us a more elaborate comparison between NOCUST and Plasma?
Okay. It's a very close-up comparison.
So like the main
Right.
differences and...
Okay, so this was also something that was not very clear from the first time that NOCUST was proposed, and a lot of people actually did refer to it as another version of Plasma. But it really starts from the core. If you look at any Plasma protocol, the first thing you see is a UTXO ledger. Here, the first thing you see is actually a set of accounts that is represented using an augmented Merkle tree. The augmentation here is just a set of intervals, and what this allows you to do is to guarantee exclusive allotment of funds to someone. So the verification algorithm for a path in this interval Merkle tree doesn't simply hash data along the way. It also checks that the interval of every leaf and every internal node does not intersect with its neighbor. And if you're interested in the proof of why that makes any sense, that is included in the paper. But essentially, no valid instance of this structure can actually have an overlapping interval. And the size of this interval basically determines your account balance. So the more transactions you do in Plasma, the larger the history of one coin becomes, or the harder, or the more effort it takes to verify something, or the lengthier your challenge response game becomes of when was this spent, who owns this now, and then you go back through the history. In NOCUST, this isn't the case. The only thing you are immediately concerned with is the immediate transition from one state to the other. What was my balance last commitment? What is my balance now? And the proofs to dispute this or to resolve this dispute are always only related to the number of users logarithmically. It's only related to how large your membership proof or exclusive allotment proof is. So with time, this ledger does not grow as much as a Plasma ledger would. And then you have the accounting model. In Plasma, you have coins that are spent. You have a UTXO ledger, basically. Here you have, ironically, an Ethereum ledger. So in Plasma, you have a Bitcoin ledger. In NOCUST, you have an Ethereum ledger inside Ethereum. So you only have accounts and their balances. And this component is completely different. So in Plasma, you're disputing whether a coin was spent, someone is exiting with this asset. In NOCUST, you're disputing completely different things. You're disputing the total balance of one account. You're disputing the delivery of one transfer. One can make the argument that maybe the transfer delivery challenges are similar to the ownership transition proofs that are presented in Plasma. This is also not the case because this challenge for transfer delivery isn't done to explore like who is the latest person. It's not actually an interactive challenge. It's just a proof that this was not delivered. It's a non-interactive challenge. And then all the reasoning you have to do about the protocol is sort of different. We have this requirement that there should be a minimum period and of course a maximum one between commitments. In Plasma, you can just keep producing blocks, right, at no fixed rate. So if you ask me, it's a different protocol. If you ask a Plasma enthusiast, it's a Plasma protocol. It really depends on what you want to define as a notion of Plasma. But relating to what was actually been described fully and what was implemented, I would separate this as its own. Not just because it's mine, because the specification that whatever commits something to a blockchain also overlaps with the specification for state channels and payment channels, and then you have to ask yourself, are those, are you using the word Plasma concretely or loosely? It just depends on, what you want to do.
How is this different from a sidechain architecture?
A sidechain needs consensus. This just uses the parent chain.
That's only the
Yes, more or less. The core difference. And then everything else is consequential of this. Sorry.
What is the interval? I don't have this is some technical terminology I didn't capture. Like what, is it an interval over some space?
Yes, it's an imaginary space that represents the total amount of funds that is managed by this contract. And then this space, if you look at it as a pie chart, is then further divided into exclusive allotments for every account owner.
So it's a single dimensional.
It's one dimension.
What is in the usage for this in the target audience? Is that micropayments or? Micropayments
and nano payments. And of course, how cost effective you want to be. Perhaps you are comfortable paying for micropayments the on-chain broadcast cost, or perhaps you're not. So it really depends on what kinds of guarantees you want. But the target audience is definitely not doing a transaction that is over 100 Ether on-chain, or something that would actually just not be too much of an issue doing on-chain.
You don't have that assumption of completely online mobile players, right? Because that's the state channels. Here, there's nothing like that.
No, players are only asked to be online once every period of time, not always online. So one advantage here compared to state channels is that a recipient can be offline. You can do a payment as a sender and the recipient can be offline, and all they have to do next turn or before or after the new commitment was submitted is come online and ask for their proof of exclusive allotment. If they don't receive this proof, they go into the data availability challenge.
Right. Thanks.
Okay. All right, we're good with time. If there are no more questions, I give it up to Olivier.
Yeah, let's give another round of applause for the. Thank you.